question 4 is a proof by induction, and this is a series proof. Okay, so let's have a look. Proof by induction, we've got to do basis step. So step 1, basis step, n is equal to 1. So let's sub in n equals 1 on the left hand side. And so we're doing the sum from r equals 1 up until 1 of r2 to the r. And if I sub in 1 into that, I'm going to get 1 times by 2 to the power 1, which is 2. And if I sub in 1 into the right hand side, then I'm going to get 2 times 1 plus 1 minus 1, 2 to the power 1. 1 minus 1 is 0, so that bit just disappears. So it's just 2 times 1, which is 2. And this is equal to the left hand side, therefore true for n equals 1. Next, we've got our assumption step, so we can assume true for n equals k. And if we're assuming true for n equals k, that means that the sum from r equals 1 up until k of r2 to the r is equal to 2 brackets 1 plus k minus 1, 2 to the power k. Right, so now we've done our assumption step, well, that's step 2. Step 3, let's consider n equals k plus 1. Okay, so always, generally with a good idea when we're doing this proof bit and this inductive step is knowing what you're looking for in your answer. So we're going to be doing the sum from r equals 1 up until k plus 1 of r2 to the power r. And what we want to get as an answer, I'm just going to write it on the right hand side over here. What I want to get as an answer is 2, 1 plus k plus 1 minus 1 times by 2 to the power k plus 1. So I'm looking for something that's going to be like that, look like that, or look exactly like that. So how do we do this? Because it's a sum of series, we always do this as, let's split it up from 1 to k. And the reason we do that is because of our assumption step. And then we add the k plus 1th term. So the sequence itself was r2 to the r. So the k plus 1 term is going to be k plus 1, 2 to the power k plus 1. And we know that the sum from 1 to k, using our assumption step, was 2 brackets 1 plus k minus 1, 2 to the k. Okay, right. Now I've got a 2 to the k here, but I've got 2 to the power k plus 1. Now the answer has a 2 to the power k plus 1, so you could convert them both to the power 2 to the k plus 1. I prefer to go with just 2 to the k. That's a personal preference. So I'm going to convert the second one into power k plus 1. Power k. So I'm going to leave this as it is. And this 2 to the power k plus 1 is going to become 2 to the k times by 2. Now I can see that there's a 2 times here and a 2 times here, so I'm going to factorize that, similar to what we were doing in our series question in question number 1. So factorize that out, big square bracket. Now I've got the 1 plus k minus 1 times by 2 to the k plus k plus 1 times by 2 to the k. Now both of the second and third terms have got 2 to the k in them. So let's take out 2 to the k. The first bit I'm left with k minus 1. And then the second one, I've got a k plus 1. And if I simplify this, clean this up, I'm going to get 2 to the k times by and it looks like 2k. Now, all we need to do is try and make it look like the answer we want. So I'm going to get 2 to the k times by 2 times by k. And now this bit here, that's 2 to the power k plus 1, isn't it? And then that's times by k. Well, with the k, I could write the k as k plus 1 minus 1. 2 to the power k plus 1. And if I look back at my thing, is that not just n minus 1? 2 to the power n, as it was where we wanted it over here. K plus 1 minus 1, 2 to the power k plus 1, which is exactly what we wanted, and that's like that. So therefore, true for n equals k plus 1, based on assumption of n equals k, shown true for n equals 1, therefore by mathematical induction, true for all n equals k, where k is a positive integer. Okay.